Hi, everyone. Welcome to Azure Cosmos DB Live TV. I'm Mark Brown, episode 20. We've got Andrew Liu here with us this week. Hi, Andrew. How are you?
Hey, everyone. Nice to be here.
Yeah, good to have you on. This is your first time on, so glad we could finally get you on board here. I think I've had Thomas on like 3 times already, maybe 4.
Wow.
Actually. I know. He has so many things he owns. There's all these features he owns, and they're all either going preview or GA. It seems like all at once. So he's been on quite a bit. Tim as well has also been on a bunch of times, talking about all the query and indexing stuff, integrated cache. I think we did a change feed episode with him as well. So anyway, welcome. Good to have you on. How you been?
Hey, great. Yeah, sounds like I've been missing out. I guess we've had lots of new feature releases that it's been maybe overdue for us to also like reminisce and kind of go through the history of the product and kind of how we got here, huh?
Well, that's why I wanted to have you on. I remember when I first met you, it was years ago. I was the Azure MVP product group lead, and I think the PMM for Antares, or what's now Azure Web Apps, in there, and was organizing an MVP summit, and had you come and talk. And so why don't you tell the folks here that don't know you kind of just a little history about you and your life at Microsoft and what you've been doing, because I think you were like maybe the first PM or at least one of the founding folks on that team, weren't you?
I've joined early. Maybe this is it's crazy to think how time has flown. So yeah, I've been working on Azure Cosmos DB for about the past 8 years now. I started my career before Cosmos DB as a software engineer, moved over to Cosmos DB to do more of a product management. It's actually had its own evolution from when we initially launched the service, it was known as Azure Document DB. And then as time went on, we went through this growth stage where we quickly outgrew the document-oriented data model. And as we outgrew the document-oriented data model, we started to realize, well, it doesn't make sense to have a multi-model database that spans beyond just the document structure and call it Document DB. And so as the service has grown, it grew into what is now known as Azure Cosmos DB. And yeah, it's been a wonderful journey. Over the years, we've improved the queryability, the elasticity, the replication, HA features. So it's been an awesome journey with that. And I figure today maybe we'll maybe talk a little bit on how we got here. And not just in the context of Azure Cosmos DB, but I figure just like, hey, I remember this was something that when I joined 8 years ago, I was like, hey, why even look at a non-relational database? Why is this even a category of databases here?
It's funny. I get that question so often from customers or just developers that are just new and have got years or even decades of experience using products like SQL or MySQL or Postgres. And they're like, why would I use a database like Cosmos? And typically I talk about like, why were NoSQL databases created in the first place, right? And I think that's a kind of a fascinating place to talk or to start, I guess, in our conversation. They've been around for a little over a decade now. Correct me if I'm wrong. Was Mongo the first in this space?
No, the history actually goes much further back into the early 2000s. And this is when you saw kind of the early pains where tech giants were outgrowing their relational databases. A lot of the challenges on why, like the motivating reason on why NoSQL databases became a thing was it turns out that scaling is hard. is a very short summary of that. But when we look at a background on this, like specifically, like what are the things that were painful with relational databases in the early 2000s was effectively it boiled down to scale out. If I go back into like the 80s, the 90s, our primary mechanism of scaling was scale up. And it wasn't just databases, like software in general if I were, and hardware, we were all in a scale-up race. Like if I look at CPUs, like throughout from 80s to the year 2000, we were in the gigahertz race. Well, initially it was first, let's break 100 megahertz, then let's break a gigahertz, and can we get to multi-gigahertz? Eventually you hit this thermal barrier where the TDP, the rate at which you can dissipate the energy you put into the processor as clock speeds increase, you hit kind of a wall. And so processors were kind of like a pretty good analogy in terms of we were in this scale-up race, and then eventually we hit this wall. And in order to continue to improve the throughput at which we could run executions against a processor, we started looking at, well, can we run multiple threads on the processor? Can we do out-of-order execution, in-order completion, and get really sophisticated with that so that we can have, for example, hyper-threading and just high, just a bunch of concurrent threads really taking advantage of a well-pipelined processor. This extends to databases too. Like in the 80s and 90s, think about like the internet in that era. Like I still have, actually, I don't know if my old GeoCities sites are still around, but web was fairly static. We built mostly these apps where it's like, static HTML, CSS, JavaScript, or actually JavaScript was in its infancy and CSS hadn't been around yet. So it was largely just HTML.
Right.
And you honestly had to be some pretty sophisticated developers to add some dynamic content to your website. It might have been in the form of DHTML, and creating XHR requests to actually have some kind of persistence layer or statefulness to your application was pretty advanced stuff. And
yeah, you're giving me flashbacks to the 90s. I did stuff like that back then. That's, wow. I hadn't thought about that stuff in 30 years.
So if I go to circa 90s, the way we scale, like I'll jump over to a whiteboard, is I put a database, let's say on a box, right? And a lot of times my box is actually running multiple things. Maybe I'm running Apache plus MySQL on a LAMP stack, or maybe I'm doing IIS with SQL Server. But more or less, like when I hit scale limits, the CPU is running high, memory is running high, I'm out of IO, is just go bigger box, right? Like get more CPU, get more memory, maybe hit up a RAID array to get more throughput. That's all good and all until you have the biggest box on the market. The challenge here is eventually you do hit a wall, and the wall is just whatever hardware is available. And so if I fast forward to the early 2000s, you saw kind of the early genesis of, well, how would we solve, more and more companies were getting larger and larger data estates, and especially within the tech giant community. There's techniques for actually handling this in a relational database, right? Like when we scale up, we could also scale out a relational database, and all we do here is the trick isn't too magical. It's just go buy a second box. But as we build a second box, you end up with the partitioning problem. So if I scale out and instead of having one box, I run, let's say, two boxes, I would run a relational database on node 1 and a relational database on node 2. I partition my data, half of it on the first node, half of the data on the second node. This is more of the sharding problem. Sharding problem is basically I have run, let's say I have some pieces of data. I'm going to just color them. Let's say I have like my red and blue data over here, my green and rainbow data over here. Rainbow data being the coolest data. You can scale your storage and your write throughput by scaling across a set of machines. You can also scale your read throughput by copying that data, right? So if I go and copy that data from machine 1 to, let's say, 1 prime, and likewise 2 prime, I can go and load balance my reads across a set of replicas and my writes across a set of shards.
Right. So you can have compute dedicated for the types of operations you want to do on that, so that you're not congesting on a single box. So it's another way you can distribute that load, if you will, right?
Now, here are some of the pain points on trying to scale out a relational database. Number one was, well, and we can break this actually into two categories. There's a set of challenges during design time, and there's a set of challenges that happen at runtime. And so design time problems are things like, hey, well, it actually turns out that in order for me, let's say Alice's data is on shard 1, and Bob's data is on shard 2. When I run a query for Alice, I need to be able to actually hit the node that had Alice's data. I need to do the routing problem.
Yep.
Now, routing initially is thought of as a runtime, but then you actually have to come up with a partition strategy, a shard strategy on, well, how do I deterministically route the request onto shard 1 or shard 2, depending on the context of that request. Otherwise, I mean, there's another solution is if you don't know how to route, you do a fan out, which is you hit every node. But if you're running every request on every node, well, you're back to the same problem, which is I can't scale all of my nodes, at least up infinitely. The other challenges that we ran into from a relational standpoint is it turns out that when you do joins, we've perfected joins within the context of a single shard. There's a bunch of algorithms on how we do a hash join and we do query planning. It's decades of maturity. But one of the things that's really expensive is cross-machine coordination. So if like I need to join a data set on machine 1 to machine 2 to machine 3 to machine 4. And as you go and do these cross products across machines, well, there's just a lot of machine-to-machine coordination for doing that join. And the analytics side, and this is where I'd actually break up two use cases. From a use cases perspective, there's a set of use cases that are a bit more transactional in nature. This is what most people like to use the acronym OLTP, but it really is just transactional processing versus OLAP, which is analytical processing.
Yep.
And when we look at OLAP scenarios, actually the join problem isn't too scary. What we do is, given the high degree of machine-to-machine coordination, let's optimize that. Let's parallelize how we think about joining across these machines. Typically, you can almost think of it as, and this is kind of the evolution of the MapReduce and big data technologies, is you're breaking it up into a sequence of mapping steps, reducing steps, and shuffle steps. You can do this when your latency is very forgiving. Like if a query, if it takes an hour, it takes an hour. If it takes a minute, it takes a minute. And what you're doing is you're just bombarding all of the machine resources on a handful of requests to do this orchestration. The challenge has been on the OLTP side, the transactional side, is what if I have a live-facing website? When I do these joins, they're really expensive, and I want to drive a high rate of request volume, lots of concurrent requests. They need to also respond very quickly. Like if the page takes an hour to load, I bet you the person, by the time you've kicked off the query and are halfway done, users already hit back button and is somewhere else. It really doesn't matter if it's 30 minutes or an hour or 2 hours. The result is the same. The user is bounced, going, hey, I'm not sticking around. So those are some of the challenges that, well, okay. How do we solve that? And how we solve that in the relational world was don't use any relational features. You denormalize all of the data into a single shard to avoid doing cross products across shards. You also scope the transactions. Coordinating a two-phase commit and locking multiple servers kills your current concurrency, it kills your latency. So just scope everything to a single node. The other side of this is a set of runtime challenges, which is, hey, what happens when the database elastically grows? Let's say shard 2 is starting to fill up. I need to actually divide the state. Like, let's say the green data has gotten so heavy, gotten so much traffic, that, and same with the rainbow data here, that effectively what I need to do is just go and carve this up such that I have two child nodes here. Let's call it 2 double prime A and 2 double prime B, such that I'm basically going to divide that state. The shard management is actually pretty tricky on how to do this as an online operation. Typically, if I look at newer websites, when's the last time you saw, like, for example, Google have a, sorry, we're going to be offline on Saturday to Sunday from 2 a.m. to 10 a.m. This is just we're running some patches. Like downtime is generally not acceptable. So
Yep.
you want to do the state management and elastically scaling, going from n nodes to n+1 nodes, while keeping availability. And then the other thing that was challenging in this space was schema management. Hey, I just want to, I have, my database is fine. I have, let's say, 10 shards replicated 3 ways. I'm building an application. I'm adding a feature. I need to be able to query off of these new attributes, alter tables, create index across 10 shards, across 3 replicas. If every single one of these is authoritative on what the data model is, and you have a little application server also saying what the data model should be, well, you basically have many sources of truth. The app, you have a fleet of app servers who all believe they know what the data model should look like. And then you also have a bunch of instances, shards, and replicas who also each are rigid in schema and also going, hey, whoa, 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 what's this new property you're trying to query off of? That does not exist. Reject that request.
Yeah.
It was just a really hard thing to do from a DevOps perspective as your app evolved. So that kind of brings us to the first wave of NoSQL databases. The first wave of NoSQL databases were there to solve the sharding and replication problem. Well, what if we simplified this? Okay, joins are anti-patterns, or at least joins across shards are anti-patterns. Transactions across shards are anti-patterns. What if we just distill this down into dumb key value stores? And if I go into like the early 2000s, you basically saw first wave where tech giants like Google moved on from implementations on MySQL to build Bigtable.
Yep.
You saw Amazon invest in technologies like Dynamo, the original Dynamo paper.
Yep.
And you saw companies like Facebook go down the path of building things like Apache, what eventually became Apache Cassandra. And you saw companies like Yahoo. This is back when Yahoo was still a top-tier search engine. Build things like, well, effectively they invested in the Hadoop ecosystem. And on the NoSQL side, you saw things like HBase.
Yeah.
And if I were to look at kind of categorizing it, all of these were really, really nice stores that handled sharding, the sharding problem and replication problem really well. What they lacked was queryability. These were largely just dumb key value data stores. And it turns out that there's actually a middle ground. And this is going to be a continuing evolution. But if I fast forward into the year, let's say 2010s and into the 2020s, in the 2010s, an interesting thing happened was it turns out people go, hey, you know what? I actually really like queries. What good is a database?
It's a database.
The whole point of a database is to write data, read data, and be able to retrieve that data efficiently. And it turns out that when you can't have a rich query surface area, it's very limiting in terms of the usefulness that the database can provide. It's great and all that it can store a bunch of crap, but I would love to be able to query that. And so in the 2010s, you actually saw a huge wave of kind of like a second generation of NoSQL data stores. And Microsoft at this point had also been investing. We actually had this thing called table storage in the early days of Azure.
Yeah.
So we also saw this problem. 2010s was actually when Microsoft had a big transformation as a company. We went from selling largely a business on boxed software, where we would go like write some software, mint a CD, give you the CD, give you a CD key, and we started moving towards the cloud. Instead of buying Office on a minted CD, you started seeing things like, oh, I could get a cloud version of Office, and that actually enables a whole nother set of scenarios around collaboration. And as we build these, as we shifted into cloud, one of the big drivers, there's actually a few themes that drive data volume and request volume. One of them is multi-tenancy. When you mint a CD, you only need to support a user of one. When you move into cloud, you need to support user bases, at least for each instance, much greater than one. And that basically the number of users you have is the multiplier in terms of how much requests per second a system needs to support and how much data something needs to support. And so you saw the second wave of NoSQL databases really focus on queryability. And this is where you saw things like document stores really start to proliferate.
Yeah. So that's kind of, and that's about that 2010 is when Mongo initially surfaced.
Yep, you would see things like MongoDB, and they actually started pivoting on different value propositions. It wasn't just the scale problem. It turns out that when you relax the schema and give some freedom to solve the schema management problem across a set of distributed servers, you started to see things like, hey, it actually turns out that when you don't have to manage two distinct sources of truth on the database side and on the app side, that you can actually iterate really quickly when the app becomes authoritative on the schema. And so this is a lot of the, I hate the word schema, schema-free or no schema, because schema never goes away. What you're really doing is you're just making it so that the database and the application no longer fight each other on being the source of truth. You're just deferring application is now source of truth. But you saw kind of this wave of, well, this is actually really nice from a developer productivity standpoint. Mongo also had its roots. A lot of the original early founders were from DoubleClick. They had come from startups needing to bootstrap things quickly and saw a need from a developer productivity side. And likewise, Microsoft also started investing aggressively into something to support our own internal offerings. This is, building Office as a cloud product, Xbox Live, Azure itself, as well as a lot of the backend services, like doing a large commerce platform for a bunch of cloud products, all needed something that had a blend of both queryability and elasticity. So you also saw a proliferation of a few other paradigms. You saw a good number of graph stores come out. Most of these took a different approach where not all of them are scale-out databases, but what they do in common is, well, can we represent relationships another way rather than having everything as a dumb key value store or a document store? We want to be able to do relationships, and maybe we can do some denormalization, but rather than doing a cross-product like a relational database, perhaps we can be a bit more efficient where we can actually store like hard physical links, reference. This is effectively vertices and edges, where I don't need to have, let's say, n entries in a table cross-product with m entries in another table. I could actually just tell you this row has a hard link to this row. And so when you do these traversals, you don't have to think about, oh, wow, how am I going to do this expensive cross-product? You just go, no. This piece of data just points to this other piece of data, points to this other piece of data. And the traversals are actually very light in nature. It's a very friendly way for later on when you want to coordinate a set of relationships across a fleet of servers. It can effectively be just a series of point lookups.
What's interesting is, going back to those early 2000s, those were all big internet companies that were trying to solve, big data issues and also solve availability challenges around that. I mean, you can't, the Yahoos and the Googles and the Facebooks, you just can't go down, right? And they needed to find a way to handle that massive volume of data, right? Because they're ingesting tons of data. And you point to the DoubleClick guys as well. I mean, they're also trying to solve that same problem, but came at it with more of a better developer productivity, if you will. Like Mongo is easy to use. And I know back in early or in mid 2000s, a lot of my PHP and JavaScript friends just loved it because it was so easy to get started and use it in their web apps. It just seemed kind of like tailor-made. You want to have a dynamic web app, you could use Mongo to power that website in there and just basically store the data as you used it, because it's basically a document store, right? And a web page is a document.
Exactly. And so those were actually the big trend I saw in the 2010s was rather than having to be a Google, Amazon, Facebook, Microsoft, Yahoo, what we saw was it turns out that everyone was getting a lot more content now.
Yep.
One was, if I look at it in terms of the two themes, replication and sharding. The big motivating reason why everyone wanted replication suddenly was availability. Patch Tuesday was no longer something that everyone wanted to go through. And likewise, if a data center went down, in a very real sense, as you move from brick and mortar business models into an e-commerce business model, the worst thing to have happen to you is when you have a 10x surge in traffic, you have an outage and you lose all of that traffic and all of that order volume. You don't want that order volume to disappear. It is a direct revenue loss.
Yep.
And on the sharding side, the other thing we saw was, of course, with e-commerce, you're basically consolidating your user base instead of things that need to scale to support an order flow from a single store. It's like having 1,000 stores in one. The volume of customers is high, so the request volume is high. And can you get predictable latency as you scale the amount of storage and compute? And the third thing I saw was it wasn't just in retail. The other space that tended to move very quickly into the non-relational space was manufacturers. And a lot of this was, the birth of this is IoT. And what I think I find very interesting about IoT is it's one of those things where like I feel like big data as a word for people who aren't, let's say, in an IoT industry or in a few of these industries, you tend to think of the different examples. Like what most people I find think about is like, players like Facebook, Instagram, social products, Twitter. But honestly, if you think about like just how many times do you actually tweet a day? And I know, Mike, you're a pretty big Twitter user. You might tweet like 10, 20 times a day.
Oh, yeah.
But if I just bring a little device, like let's say this phone, and I want to do telemetry off of this, in 1 minute, if you're doing a real-time telemetry scenario where it goes, here's my state, here's my state, here's my state, here's my state, if I do a second interval for producing a piece of data in 60 seconds and 1 minute, this little device has produced more data points than I will tweet all day.
Yep.
And so if I now multiply this by the fleet of devices, and what we're seeing is, especially industrial use cases, things like assembly lines. Hey, we want to make sure that from an assembly line perspective, this is where like technology meets real business value for not just in tech giants, but in a number of different industry use cases. Is most costly thing for I can have in an assembly line is assembly line stops. The machine broke. I have to take this thing offline. And so what you're doing is you're actually monitoring things like machine health across all of the robotics on an assembly line. And likewise, from a supply chain perspective, as you manage a fleet of, let's say, vehicles, or on a construction site, you want to make sure that your generators aren't just walking off. Someone snuck into the the construction site at night and started wheeling away all of your equipment. You want to have these regular heartbeats on all of these devices to do things like geofencing, to understand the location of everything. Are my trucks for my supply chain on time, or do I need to do some dynamic, load balancing on how I think about different parts on a bill of materials? This whole IoT side of the equation was what I found like truly like large scale data, just because machines turns out they just produce data at a much faster rate than humans do.
Hey, I had a question from a viewer, speaking of kind of like industry specific, but a question around use of these types of database systems for, say, financial services or like for banking systems. So I guess the question is, do you think core banking systems would benefit from these types of systems?
Yes.
Type of database?
So what I'm noticing is there's a few industries that or in the early 2010s, I didn't see as much usage on non-relational systems, but as we entered the 2010s, I actually saw a few that are starting to pop up more and more. And maybe 2020s is a bit late, late 2010s. I saw payments actually as a fairly common use case start to pop up. Less so on the sharding side and more on the replication side. These tend to be mission critical solutions. Like if if you're going to move a large volume of transactions, historically what we would do is we'd either be a little slow on like accept a transaction and then process it later. But as these things become more real time, and you want the latency of clearing a transaction to be much faster, these are mission critical systems. They do need to support very rich replication.
Yep.
And then from a sharding perspective, as you aggregate, we are also seeing a lot of consolidation. I mean, things like credit cards are now even becoming old as we move from checking to credit cards to like mobile payments and online payment solutions. Those have been some driving factors on the financial services side and banking. The other side of it is also we've seen, for good reason, a lot more scrutiny in terms of how investment banks, after they take in all this money, reinvest that money. I mean, we've seen global financial crises over the last couple of decades. And some of the things that they also do now is from a risk management perspective, when you do risk calculation on balancing a portfolio with all of this cash that's in reserves, the amount of data processing and the amount of signals that go into that is also growing at a fairly rapid rate. The other industry I would say has been interesting is healthcare. A lot of the big theme there is interoperability. And there's actually a new standard here. It's not a new standard, but it's one that's getting increasing adoption is FHIR, FHIR.
Yeah.
And what this is all about is historically, like just for folks who aren't in healthcare, think of it as you're at your doctor and you have, let's say, an illness where you require a specialist. And in order for you to see a specialist, it turns out that in your network of doctors, they just don't have that particular specialist. So they need to transfer you from one medical system into another healthcare system, another network of doctors in a hospital system. Patient health records used to be something that was just very, very difficult to transfer from one healthcare provider to another healthcare provider. Like people would literally mint CDs, put your like DICOM images on it, and FedEx it over, along with a set of manila envelopes.
Oh, and don't forget a fax as well.
Or fax it over.
Yeah, fax it over.
And one of the things that's been propagating is the healthcare industry is aligning on, well, how do we share patient health records across each other and achieve some interoperability across all these disparate systems? Is they've agreed on a schema, FHIR, which actually takes advantage of, it is JSON, it's a document-oriented structure. And that's also seeing a big wave as like the number of healthcare records, since it's not siloed anymore, you have more of an aggregate across providers. The volume grows, as well as the from a structure perspective, because you need some flexibility. These have been motivating reasons why I've noticed FSI and healthcare start to become increasingly larger adopters of NoSQL databases.
You know, it's interesting. There's kind of a growing trend, if you will, around standardizing kind of industry schemas, if you will.
Yep.
Not just healthcare, but other systems as well. And I know there's a team here at Microsoft that's kind of working on that and trying to help build that into kind of the data governance solutions. We've got the common data model. That's right. And it's funny, you know, FHIR, even though it's basically relevant to a document data store, it's a NoSQL database, but it's a schema on a NoSchema or a schema agnostic database, if you will. So you're right. You know, schema doesn't go away, right? You have to have something to describe the data. And here you've got a kind of a growing industry standard around that to help with interoperability, like you say. So yeah, it's just an interesting area. I think you know, I had Lena Hall on a couple of weeks ago, and we kind of talked about some of the industry trends, and we touched on that, I think, just briefly. But yeah, interesting.
Yeah, and I guess for folks who haven't seen CDM, some of the context around that has been same thing, interoperability. Especially we're looking at it a little bit less on the healthcare side and a little bit more on software ecosystem side. Especially like CRM platforms, Dynamics is actually the first to onboard CDM. And context around that is you end up to orchestrate, for example, a CRM platform or a HR recruiting platform. You tend to have a lot of different software you use, and the interoperability across those is low. And if you have N pieces of software that need to figure out interoperability across N-1 other pieces of software, the number of permutations is just really high. It scales on order of N squared. The other way of solving that is you align on a common data model. If everyone speaks a similar or a fairly agreed upon schema, you don't need to actually coordinate with N-1 other vendors. You can just go ahead and implement based off of a structure that everyone else is expecting, and the interoperability planes there become or they largely become much lesser, right? The pain points are they go away. I wouldn't say completely go away, but it does help with the coordination. I figure some of the things that, like, these are trends we saw. I figure I'd also go a little bit into architecture and the behind the scenes view on how we solve it.
Yep. I think people will be fascinated on understanding more. I mean, as a developer, I want to know how a product or a service is built because it helps me understand the behaviors. Customers may also wonder why we did certain things the way we did. I know, we touched on it earlier, right? So Cosmos started as document DB. It was not a multi-model database initially, but then we added multi-model capabilities. I think Mongo was the first, correct?
I would give more credit towards Cosmos DB, especially with how I think how true multi-model is. Like in some sense, you could say even the first document stores were all multi-model, since key value stores are every document store is effectively a key value store. You just turn off indexing and you disable your query engine, and you have a key value store. But I think some of the more innovative things is blurring the lines between some of these graph data stores with document stores, as well as columnar stores. And these are things that I didn't really see outside of Cosmos DB until, we did the big launch. But some of around like the 2017, late 2010s, I would say the high-level themes that started becoming apparent is because data has become increasingly siloed with specialized databases, there is a desire to try to break down some of these silos just so that different teams within an organization have a bit more interoperability, kind of similar to the interoperability pains that I was talking about earlier, but at a more micro level within an organization. Multi-model does help a lot with that. One of the big things that actually was a huge innovation is I would put a category of data models, document, key value, and graph all in the same bucket, which is they're optimized for seek queries, OLTP queries, where you're trying to find a needle in a haystack. Like, find me records where first name equals Andrew. And then you have a set of data models that tend to be a bit more optimized for scans, for OLAP. And when you look at the columnar data model, what you're doing there is, it turns out that if I have, let's say, 10 properties within a record, let's say, you can think of it as a row, a document key value or a vertice or an edge, you can think of as a row, and you're finding which row within this table I'm trying to pull out. A columnar data set is, it turns out that if I want to do, let's say, the average temperature in an IoT scenario, I really don't care about all of the other device metadata. If I'm calculating the aggregate, whether it's an average, min, max, median, 99th percentile, what you're doing is you're doing a scan on a single property. And if I were to lay out, like, here's a bunch of rows where I have and columns, rather than saying, hey, which row do I want based off of a filter predicate, what I really want to do is look across rows and calculate an aggregate based off of a column of values. And if I have to read the entire row, given, let's say, 10 properties, and I'm only reading 1 out of 10. The IOPS on the machine is actually just very wasteful. For every, let's say, kilobyte I read, I'm discarding 900 bytes. That's not really an efficient way to leverage your machine resources. So what a columnar data store does is it lays out the physical layout on the disk such that each column is co-located onto the block as opposed to each row.
Yeah.
And that way, when you do scans, they're a lot more IOP efficient.
Mm-hmm.
And some of the huge themes we saw with Cosmos DB is as we moved into multi-model, we supported actually an aggregate of these as well as multiple representations. So a good example is how we're looking at Synapse Link with Cosmos DB. As a user, I want to be able to run a transactional workload, but I also want to do analytics. And the historical way in the absence of multi-model databases is I would have a transactional store. I would run ETL jobs when the traffic was low into an analytical system. And whenever I do a schema update, my ETL job would break because the schema has changed. There was also some latency added on what frequency you run these. You try to speed these up with techniques like micro batching or stream processing, but honestly, the latency is high. And what we saw was an investment, like the themes are multi-model, HTAP, as well as serverless.
Mm-hmm.
That I would say in the late 2010s. HTAP, what we did was we made a pretty big bet, and it aligns well with the multi-model direction, is having both simultaneously a transactional layout and an analytical layout, so that you're actually covering a gambit where no matter whether a use case is transactional, analytical, or both, and really the category is both, you can do analytics in real time on the database by just having different layouts on the same data set on the disk. We saw that with HTAP. And then the serverless is another theme, I would say, in the late 2010s. Not something that is directly related with multi-model or HTAP, but really plays more into the elasticity of a lot of these non-relational databases, which is, hey, elasticity is great when my traffic patterns, if I look at a traffic pattern where, let's say, y-axis is the request rate per second, and x-axis is time and y-axis is request volume.
Mm-hmm.
When you see these peaks and valleys, you could try to shrink and grow the cluster dynamically. But depending on the latency, like if your system is something that takes a bit longer to respond, you have a set of waste here. And as elasticity really got perfected by those who do it really well, I wouldn't say everyone who knows how to shard or promises elasticity is the same. You can actually measure the quality of the elasticity by the latency on how well they're able to hit different peaks and valleys in that demand. And this is something where the ones who do it really well started exploiting this by building, instead of a per node business model for how you think about databases and pay for databases, you can do it on a pay per request basis. Because what happens is you can very frugally manage the backend infrastructure on that superior elasticity.
And that's what we're doing, because we're a multi-tenant service, right? So with resource governance and all of the other things. So that's why we're able to do this type of serverless offering, as well as the auto scale as well kind of falls into that. And I'll point out too is, these same customers like retail and payment processors and others also need elasticity in addition to low latency, in addition to availability. Oftentimes, you don't know when things are just going to blow up in terms of like a sale on something. Who knows, right? Things can go viral, and all of a sudden they're getting requests from clients, but purchasing stuff or whatever like that. So being able to handle that and not have to turn customers away, because like you said, it's, if you can't complete the sale, it's pretty much the same as being down, if you will. And for people like retailers, the opportunity cost is too high. And people, just having the kind of the pay per request, some people just really like that, right?
It allows you to take advantage of, a lot of people think initially, and this was true, like in the big table days, like the only people who would need a non-relational database were people who truly needed to solve the sharding problem. Like you needed to be one of like the Fortune 5 or Fortune 100 like top largest companies. But what serverless allows you to do is it actually allows workloads that start small, grow large without having to do like a V1, V2 rewrite at some point when you grow and hit scalability planes. The elasticity there with auto scaling, with serverless gives you a lot of flexible freedom so that if you want to go and future-proof an application such that you want great, cost effectiveness and total cost of ownership of a solution as you start small and grow large over time, it gives that flexibility as a developer.
Yep. And I think it meshes well with kind of the promise of just the cloud itself, right? In that the cloud democratizes the availability of compute and storage and all of these things. Serverless is kind of the complete fulfillment of that, if you will, because you don't have to go and invest a whole ton of money ahead of time to go and get your application, say it's a startup or something like that, and can grow as you grow, right? And you're only paying for what you sell or use. So, yeah.
So let's talk a little bit on what goes behind the scenes to make this possible, and then also some takeaways on how that impacts, as users of these systems, how we want to think about things like data modeling, because they actually do have artifacts where how you want to think about the data model is going to be a bit different. At a macro level, what Cosmos DB does is it provisions a database account for which you can have databases, and for which you can have containers. And we use the word containers in a very generic fashion. It's just a place to throw your data. If you're coming from a document-oriented data model, we tend to like to call these collections. If you come from a columnar model, you might call these tables. And if you come from a graph model, honestly, you'll probably call this a graph, and you have a set of vertices and edges underneath. But our data model agnostic way of referring to this is a container. What this does is when a user provisions a container or a database, depending on where your RU knob is, our RU knob is actually just an aggregate. What we're doing is we're just normalizing a set of resources that we need to run a database. That would be the CPU, the memory, the IOPS. Depending on where you've provisioned this, whether at the database level or the container level, just for sake of example, I'm going to use a container level RUs. When you do that, what we're really doing behind the scenes is we're creating a set of partitions. And we call these partitions. Think of this as the sharding problem. What we're doing is, given a placement hint that we call a partition key, what we're doing in here is a technique called consistent hashing. And consistent hashing in a nutshell is, imagine that I have a pile of data, right? Like I have a data set where I have all sorts of data, some red data, green data, blue data, rainbow data. If that data is too much to fit on one box and needs two boxes, I just go and divide that data set in half. And the way we do routing is if you provide a placement hint, let's say a partition key, in a multi-tenant system, if the tenants are small, a lot of times, like a good example of that might be a user ID, or in an IoT system, that might be a device ID. Because most of the time you're routing a request like, hey, find me things about this device or find me things about this user. What you do is you use that user ID. Let's say user ID is Alice, or it might be Bob, Carol. What we're doing is we're hashing that across, think of it as a set of hash values from min value, which would be like in hex like 0000 to max value, which is FFFFF. And as we hash to this set of values, we can just subdivide them such that the range from 0 to half goes to partition 1, and half to max goes to partition 2. And what consistent hashing allows us to do that's a little bit different from a naive hash is allows the elasticity factor. What happens when I need to grow from, let's say, 2 nodes to 3 nodes? So if I compare that to a naive hash versus a consistent hash, Imagine if I do something like, take the MD5 or some kind of hashing function, mod the number of partitions. If I take a piece of data and I'm striping it, the ID of our record, or let's say user ID is 1, 2, 3, 4, 5, and these are striped across partitions. 1, 2, 1, 2, 1, 2. When you grow that from 2 to 3, the modding will end up going 1, 2, 3, 1, 2, 3. And the thing that I want to highlight is you're moving data from machine, not just some data into machine 3, but you actually have to do this shuffle where, hey, why am I moving data from machine 2 to 1 and 1 to 2? That seems really wasteful. Does that actually allocate more compute? And the answer is no. And so what we're doing here is by taking a range of hashed values, if let's say this partition becomes a dominant one, we can go and split that partition in isolation without having to touch other partitions. And what Cosmos DB does is based off of a partition key, which is think of these as logical partitions. What we do is we might have, let's say, Alice and Carol here. And tomorrow, if Alice grows large, what we do is we can subdivide these such that Alice is here and Carol is here. Meanwhile, let's say Bob and Danny don't need to be touched. Like, you can basically flexibly grow a partition in isolation of each other. Within each of these partitions, if I zoom in, a partition actually isn't a single machine, it's a replica set. And so what we do is we create a replica set, 4 replicas per region, and we allow active-active topologies such that if you have an active-active workload where you can both write to region 1 and region 2, we do some replication and conflict resolution across these. That's at a macro level what's happening. Whenever you add a region to Cosmos DB, or remove a region, if you want to grow the number of regions for setting up geo-replication, what we're doing is within the partition, we're setting up additional replica sets and hydrating those replica sets. And then from a more macro level, what we're doing is we're elastically growing our workload from n number of partitions. And where the elasticity comes from is the fact that we can grow and shrink the number of partitions over time. Now, the replication side of it is, I think, very fascinating too. And that actually comes off with some trade-offs. It turns out that replication, just because we want to replicate, life is not always good. There are a set of trade-offs. And the trade-offs typically come in the form of, most people tend to view this in the context of CAP theorem. Yep. But really, it's just trade-offs with respect to consistency. And what ends up happening here is, in the old school days, if I look at old school databases built in the 80s, 90s, what they typically steered you towards was you have 2 modes of replication. You have asynchronous replication or you have synchronous replication. And what asynchronous replication does is you effectively have eventual consistency. And synchronous replication, you have strong consistency. Basically, if I write a piece of data on machine 1, I'm guaranteed that it's replicated on machine 2 before I acknowledge the request. The downside is this actually has a latency impact. And so your requests tend to just be a bit slower when you have synchronous. And then from a recovery time objective, from the availability side of this, you also have to cut the link at some point, because, or at least manage that. When the link is cut artificially, out of your control, not artificially, but just out of your control. Let's say you have 2 data centers and someone was just digging a hole and cut the network link. Because you're not able to propagate changes, like, hey, that red value got updated to, sorry, black value got updated to red. You basically don't know your peers, whether you have a consistent view of the world. So you're left with, do I respond to the request or do I not respond to the request? And that effectively is, in CAP theorem, the trade-off of, given a partition, a network partition P, what is the trade-off with respect to consistency, C, or availability, A? And you typically are taught, like, you must choose consistency or availability. There's actually techniques that allow you to circumvent some of these trade-offs, and that's through more advanced techniques called consensus protocols. In a consensus model, what you do is you actually look at quorum mechanisms. And in a quorum mechanism, I'll give you an example. If I have, let's say, 4 replicas, and I write to, let's say, machine 1, machine 2, machine 3, and I am unable to write to machine 4, as long as we can create, let's say, on the write path and a read path, a quorum here. Let me, oops. If I do, let's say, a quorum, maybe I'll start with an easier example. Is just like if I had 3, let me start with 3 replicas, and we'll talk about how we can grow that. Is if I successfully write out of 2 out of 3 replicas, let's say I successfully write out of these 2 replicas, and I read from 2 out of 3 replicas, it turns out that I can read from any 2 replicas, any 2 pairs. I'm going to see overlap. So like for if I read from these 2, this is going to win the tiebreaker. If I read from these 2, this one's going to read the tiebreaker. And if I read from these 2, both of them are going to have the value that I had just written. But I can actually sacrifice availability, allow a node to completely fail, as long as a majority of them were successfully written and a majority of them were successfully read from, that I can actually get both consistency and maintain a level of partition tolerance.
Yep.
Now, this is where things get a bit wacky here, is we can actually tune the quorum mechanism such that you don't have to have a uniform, always a majority on the write or a majority on the read. And this, by tuning this, we can actually get some better trade-offs. So rather than thinking of these as hard extremes of eventual and strong consistency, this is where we've also been able to do a tunable level from eventual to Cosmos DB has this thing called consistent prefix.
Yep.
Session, bounded staleness. And what we're able to do is take a combination of both the quorum mechanism as well as little techniques like log structure techniques for taking the log sequence number. Think of as if I have an op log, an operation log where I've written operations 1, 2, 3, 4, 5, they're written against a log with a log sequence number 1, 2, 3, 4, 5. And if I do a high watermark on that log sequence number, I can actually do techniques like, hey, given the, I'll give a real world scenario, a shopping cart scenario. I have, let's say, 1 million users shopping online. When Alice adds something to the cart, I actually don't need Alice's experience to be negatively impacted for replication latency because Bob added something to the cart. Alice can't even see Bob's cart. So whether Bob's cart is up to date, that data is up to date or not up to date, Alice really doesn't care to pay a performance penalty for that. What Alice cares about is that when she adds something to the cart and she refreshes the page, that item is indeed in the cart. And when she checks out, the order totals make sense. And so a nice quick stop here, a middle ground is session consistency, where rather than doing purely sync versus async mode, we could do also techniques like a log sequence number. Hey, with Alice, we know that for read and write, a high watermark, she went up to read and write operation, highest we've seen is 3. Any subsequent operation needs to reflect 3 or greater. And as long as we maintain that is true, you can actually read from a single replica majority of the time, as opposed to having to use CPU memory, or in our case, RUs across multiple machines. And so what you notice is for CAP theorem actually doesn't tell a complete story. It only talks about availability with the consistency. There's actually another theorem called PAC-LC, which is given the trade-off, given a network partition, what's the trade-off between availability and consistency? Else, what is the trade-off with latency versus consistency? And I wouldn't even say it's just latency. There's a latency and throughput trade-off here. That what we do is we give you basically models to optimize. And rather than having hard extremes, what we find is for like most multi-tenant systems, multi-user systems, and IoT systems, the session consistency actually gives you a much easier shade of gray that gives you the blend of both performance and consistency that is a lot more desirable than eventual and strong.
You know, I think it's a fascinating mix, the way we offer choices of consistency in there. You know, because session's unique in that Unlike the other consistency models that are in the that we offer, Session's a client-based one, so it's not dependent on the replication. It's not dependent on a quorum, like bounded staleness requires a quorum, if you will, because it's going to read from a minority. It's going to read out of 2 out of the 4 in there and check that LSN server side. And of course, consistent prefix is just reading it in the order it was written, right? So it's basically dependent on the data. But client or session is a client, right? So you're actually holding that LSN and then shipping that all the way to the end user, who's then just going to request the data with that same LSN, and then we'll basically read from each of those replicas until we find the one that matches within there. So it's an interesting way to provide what looks like strong consistency, but it's really read your own rights is the official kind of consistency guarantee within there.
Yeah. Or I'm doing a quick time check. I'm guessing I can't go into how each one of these is built.
I should do it.
I think we maybe have this on our docs, I think, at this point.
Yeah.
But what we can do is we can do a follow-up. Actually, for everyone who's tuning in, let's go into questions. And then what I'd love to do is actually, if you can put in questions you have about how things work behind the scenes, whether it's the automatic indexing, change feed, or other things, I'd be more than happy to do like a part 2 and dive into each of these subjects. But let's go into a round of
I do have a few questions on here. They're not strictly related to what we were talking about, but I think with regards to the consistency models, I should probably do an entire episode related to that. I used to, for those of you who don't know, this used to be my feature area, but we've got another guy on the team now that manages all of our HA. This all falls into the high availability capability. So all the replication, consistency, conflict resolution, that sort of thing, all falls into our HA set of features, if you will. So, but I do have a couple of questions. Oh, let's see. Let's pick one here. Why did Cosmos DB implement Gremlin and not Cypher?
So some of this is timing, and the other bit is open sourceness. Gremlin is an open source query traversal language. Cypher, at the time when we started, was not. Cypher is actually very proprietary, belonging to Neo4j. And at the time, when we started this, Apache Foundation was looking at, hey, looks like every single graph database vendor is coming up with their own proprietary language. Could we not standardize, kind of like what we've done with SQL or relational databases and ANSI SQL, a standard graph traversal language? So Gremlin was born out of the Apache Tinkerpop project.
Yep.
And because it had big backing around the Apache Foundation and it was the large open source graph traversal language, we made a fairly heavy bet on Gremlin.
Yeah.
If I were to look at it today, Gremlin and Cypher from an adoption level actually look pretty on par. Cypher as a proprietary language has become, quite prolific, as well as there's a lot more tooling. There's actually tooling out there to even do Cypher to Gremlin translations. And so that is something that as we, over time, continue to evolve, we've added APIs to Cosmos DB before. We will likely evaluate and look at adding additional APIs in the future. If Cypher ultimately ends up being a de facto query language for graph databases, you can expect that eventually we will make a bet on it.
Yeah.
But for the time being, because we are very open source focused, Gremlin has been where the center of gravity has been.
Yeah, and then as a follow-up, there's of course now OpenCypher.
Yep.
But that wasn't available. That wasn't
around.
That
was available in 2017 when we made a bet on Gremlin.
Right. That's right. That is more recent, if you will. Here's another question. This was something we didn't get a chance to talk about today, but if I use Gremlin API, then does Cosmos implement Graph as its backend storage?
Oh, actually, this is a very, very interesting topic. And I would love to do like a part 2 here. Effectively, Cosmos DB has a backend and also a front end. The backend, a lot of what I went over today at a more macro level, does the shard and replica management. And what we do is our query engine is actually somewhat distributed across our backend and our front end. And so a lot of the how we look at graph is because a lot of times we are partitioning a graph such that vertices and edges are striped across different backend nodes. A lot of our graph query engine is actually on the located and hosted on the front end server to be able to do cross-partition traversals. And maybe as a follow-up exercise, what we can do is we can go into like the nuts and bolts of how we've approached this.
Yeah, and maybe also we could talk about this question here is how do we manage our index structure? So I think we could talk about the inverted index that we use in the back end, which is quite novel, I think, and people would be interested in understanding how we do indexing in the back end.
Yeah. How about this? I'll give you kind of a short answer, and then we'll do a follow-up as a long answer. Short answer is what Mark is alluding to is we do use inverted indexing. And the way to think about an inverted index in a nutshell, if you haven't seen one before, is rather than creating a B tree or a log structured merge tree on each column or property, which is what a traditional index would do. And that's where, if you're used to systems where you have to do like, something like collection.create index on property A, property B, property C, or alter table create index on column A, column B, column C, rather than doing a B tree per column or property, what an inverted index does is it creates a single tree that spans across all of the properties in the record. And what we did was we, in the early days, exploited the fact that Cosmos DB tends to use self-describing schemas, especially with the document-oriented model. Each document actually tells you, here are exactly what properties I have, and here are the data types for them, in addition to the values. That what we can do is we can take a representation where we transform a document into a tree representation and merge all of those trees together, such that if I take the union or merging of those trees, that effectively is the shape of an inverted index. And as I union them, if I have overlapping documents, what you can think of as the leaf nodes being the values, they have pointers back to the actual IDs of those index posts, or think of them as index postings, but they're effectively pointers to a set of documents. And by taking that approach, we can build a automatic indexing story. So without having to ahead of time do a alter tables create index or a collection.create index, what Cosmos DB is able to do is at runtime, as documents are being fed into the system, see what the schema is, transform that into a tree, merge that into a larger, a right optimized, we call it a BW tree. There's actually a paper on that. If you look for Microsoft Research BW tree, that's the data structure we're using.
Yep.
And what we do is we layer that with an inverted index pointers back to the original records in our content store. And that, in a nutshell, is how our core indexing is done. Composite index is a little bit of a different beast. What it does is think of it as almost of a concatenation of multiple values. And why that's important is when you do queries that look something like select star from, let's say, a collection where filter predicate 1 and filter predicate 2, what the engine is doing is it's looking at the index postings for filter predicate 1 on that large tree and the index postings for filter predicate 2 and looking at the intersection of those two. Rather than having to calculate that intersection at runtime, if you were to materialize a view where your index was a union already of these two properties, you can directly query into the index and save that step, which is why when you do queries on whenever you see multiple scalar filters or just not just filters, like where A and B, as well as where A order by B, these are both types of queries where if you materialize a view where you have both properties represented, you can do a lot of query optimization such that the RU and latency of those queries are even better on a composite index as opposed to just a plain inverted index.
Yep. Yeah, good. We'll definitely have to, I you can almost do an entire show on our indexing engine in there. But good follow up for that there. Another one, yeah, request for follow up. Behind the scenes on how Cosmos uses distributed systems to make data more available. That might be interesting. We're big users of Service Fabric, in fact, and maybe that would be an interesting way of talking about how we. Well, I guess it's just as part of your talk, like on the back end. I think that would be part of it.
Yeah. If I let's keep all of these for a part 2 deeper dive.
Yeah.
The short summary right now is we look at distributed systems and replication both at a global level as well as at a per region level, and our quorum mechanisms actually are aware of that too. We have concepts of both localized quorums as well as majority quorums, and within a single data center or within a single Azure region. A lot of the architecture for Cosmos DB for replication and availability is a service fabric implementation. And then at a macro level across regions, this is where and the reason why the implementation has to be a bit different is the network links have much higher latencies and different both latency and throughput characteristics. But at a macro level, there's also a set of database specific logic for coordinating the cross-region, both the runtime of reads and writes on how those quorums are done, as well as for various high availability disaster recovery scenarios. And that's its own beast on how we look at active-active topologies, the trade-offs of that with conflict resolution, as well as how you can use that to also navigate some of the trade-offs of failover and decoupling away from having to do a failover process.
Yep. Great. Just one more question before we kind of conclude today. Is there a good book or some other resource that can help me deep dive performance tuning?
One thing I'd really love to recommend is there's a really good Pluralsight course done by, it's actually not by us, but by someone from the community, Lenny Lobel. If you look online for Pluralsight Cosmos DB from Lenny Lobel, he's a Microsoft MVP. And I found, at least personally, that to be a really, really good resource for picking up the entire surface area of Cosmos DB. Mark, are there other things that you could recommend on this?
There's definitely no books because our product moves so fast that if you wrote a book, it would be out of date by the time it hit publishing. But what we have been doing, and what I would recommend, is we've been doing a ton of work on our back end for monitoring. And I've had Stephanie on the show here a couple of times, well, at least once on the monitoring. And so there's a recent episode where Stephanie kind of goes into a lot of the new monitoring stuff we've done. But that's, because we're, a service, that's going to be kind of where performance tuning starts for you, is to actually look at the telemetry that Cosmos is emitting in terms of the usage for your application. And then going off of that to help tune the performance of your app. So I would say the monitoring docs is a good start. There's also another one as well as another show is I had Matthias on this show about a month ago, and he talked about all of the ways, well, he talked a lot about the .NET SDK, but he had a whole section in there on performance tuning on that. And also he's had multiple blog posts about performance tuning using, there's a client proxy within there. Anyway, there's a whole bunch of other knobs, bells and whistles on the Cosmos client that you can use to tune performance of your application. So I would look at our blog. It's devblogs.microsoft.com/cosmosdb. And then look at the docs on monitoring. And then look at the past episodes on YouTube and look for the one on monitoring, and then also for the one on the .NET SDK with Matthias. There's lots of good content in there with that. So yeah, well, Andrew, thank you so much. Great having you on the show finally. And look at this. you come on once, and then it's like Hotel California. You can't check out because we're going to have you back to do a follow-up episode on our front end and back end for Cosmos. So
yeah, absolutely.
Yeah, sounds good. So, hey, folks, got some announcements here. So we started a new Cosmos DB virtual user group out on Meetup, and we're going to have our very first virtual meetup on Wednesday, September 22nd, 2 p.m. Pacific time, which is 10 p.m. London or 7 a.m. Sydney. And I'm going to be the very first host for that user group. And I'm going to give a talk about modeling and partitioning data in Cosmos DB, which is an important topic if you're new to the service. Knowing how to model your data and partition your data is absolutely critical to achieving high scalability for a database like Cosmos. So come check that out. Also, we are organizing our very first Azure Serverless conference. That's going to be September 29th through the 30th. And it'll be a series of three-hour live streams in Americas, APAC, and EMEA time zones, along with some on-demand sessions as well. If you're a speaker and want to present a session, please feel free to submit. I got the link for our Sessionize page there below. And I think that's it. So next week, I'm going to have a guy on our team, Abhinav, and he's going to talk about the new Kafka connector that we built in partnership with Confluent. So come check us out next week. That'll be pretty cool. And I guess until next time, that's it. So Andrew, thank you very much for joining us this week.
And thanks everyone for tuning in.
Yep. Thank you, everyone. Take care.